Okay, so hi everybody, welcome back. Today in this video, we're going to be finishing up our Chapter 19 lecture on heat and temperature. So by the end of the video, we'll have covered everything that I wanted to cover from Chapter 19. And in fact, this is the last video of the semester where we will be covering any new content. So after this, we're just going to be reviewing for the final exam. So the first topic that I want to touch on here in this video is modes of heat transfer. So let's get into it. So let's remember what heat is in the first place. When we refer to heat, given by the variable Q, we're talking about a transfer of energy due to a temperature difference. So the classic example of this is if you have two objects with different temperatures, like a block over here that's at 300 degrees Celsius and another one over here that's at 0 degrees Celsius. If we allow them to interact, if we just touch them together, then heat is going to flow from the hot block into the cold block. So that means energy is moving into the cold block, and that will continue to happen until thermal equilibrium is reached. And then at the time when we reach thermal equilibrium, the two blocks will have the same temperature. Okay? So heat is referring to that transfer of energy from the hot block to the cold block in this example. But it turns out there are different ways that heat can flow from one place to another. In other words, there are different modes of heat transfer, and I want to go over those with you. So the three primary modes of heat transfer that we're going to discuss today are conduction, convection, and radiation. So the first mode of heat transfer that we'll discuss is convection. Now, convection is when energy is carried directly by a fluid which is moving from a high temperature region to a low temperature region. So if you have a fluid that's at a high temperature, it can simply just flow to a region of the fluid at a lower temperature, and that's how the heat gets transferred. That's convection. Now, a classic example of this is when you heat up a pot of water. So let's say there's a flame directly underneath the pot of water. The water that's directly above that flame is going to be at the highest temperature within the pot, whereas water up here is going to be at a lower temperature. That's going to cause convection within the pot. That's going to cause the water to flow from the high temperature region to the low temperature region upwards. But the water will then have to flow back down after traveling up in the center of the pot. So actually we create these circulating currents of convection within the pot. So convection is typically the dominant mode of heat transfer that you're going to find in a liquid or a gaseous material. So in the air or in a body of water, it's typically convection that's transferring heat within that material. The next mode of heat transfer that we're going to look at is conduction. So in conduction, energy is transferred via collisions between molecules, but there's no large-scale movement of matter from one place to another. When we have convection, there is a large-scale movement of matter. The fluid is actually moving from one place to another. But in conduction, that's not the case. The matter isn't moving anywhere. It's just that molecules are colliding with each other and transferring the heat that way. So typically, conduction is going to be the dominant mode of heat transfer in a solid material. So I'm going to show you an animation that illustrates the idea behind conduction. So this is some sort of solid material, and all of these just represent the different atoms within that solid material. What we're going to do is heat up the left end of it, so just put it to a flame. We'll increase the temperature at that end, and we'll have heat being conducted down the length of the material, again, via conduction. And so why is this happening? Well, when you put the flame to the left end of this material, you increase the temperature locally in that region, and you cause the atoms to jiggle around faster. But those atoms collide with the atoms right next to them and get them jiggling around faster at a higher speed than before. And that just continues on down the line. These collisions keep happening, and before too long, you have the heat being transferred from the left side of this object to the right side. But again, notice how there isn't any large-scale movement of matter. Each atom is just staying in its fixed position. It's just that they're colliding with the atoms next to them and transferring the energy down the line. That's conduction. So I'm going to show you an equation that describes heat conduction. In particular, we can calculate the rate of heat conduction, that is, the amount of energy transferred per unit time through an object, that's delta Q over delta T, using this equation. So before we get into the equation, let's just look at the setup here. So this is our object that's conducting the heat. The heat is flowing through this object, in other words. And on one side of the object, we have a high temperature region where the temperature is TH. And on the other side, the temperature is lower. Let's call this TC. So we have the hot temperature and the cold temperature on either side of the object. Now the object has a certain area A. So this is the area that the heat actually flows through. And then the thickness of the object is delta X. That's the distance through the object that the heat has to travel through. Okay? So what we have is delta Q over delta T, so the amount of heat flowing through the object per unit time, that's the rate of heat conduction, is equal to minus K times A, again A is the area, times delta T, that's the temperature difference between these two sides, divided by delta X, that's the thickness. Now K is called the thermal conductivity of the object. So it's going to depend on the material that the object is made out of. Each material has its own unique value of K, but we call that constant for the material the thermal conductivity. Now, the negative sign in this equation is telling us that the heat flows in the direction of decreasing temperature. In other words, it flows from hot to cold, not the other way around. But typically, we can just neglect the negative sign in the equation. So if we take a closer look at that equation, delta Q over delta T, that's the rate of heat conduction, equals minus K times A times delta T over delta X. Let's solve for K in the equation so we can understand what units are attached to this. So K would be equal to minus Q times delta X divided by A times delta T times delta capital T. So the lowercase t is for time, the capital T is for temperature. So what sort of units are we dealing with here? Well, Q is heat, so that's going to be measured in the standard energy unit of joules. Delta X is a length, so we use meters to measure that. A is an area, so we use square meters to measure that. Delta T, lowercase t, is a time, so we measure that in seconds. And delta uppercase T is a temperature, so we can measure this in Kelvin. So what we can immediately do is just cancel out one factor of meters, like this. And then we can notice that we can group the joules and the seconds together. So we have joules per second on top, divided by, now we have meters and Kelvin on the bottom. But I want to remind you that 1 watt is equivalent to 1 joule per second. So this is a unit of power, whereas the joule is, of course, a unit of energy. So then our units for K, the thermal conductivity, are watts per meter per Kelvin. Or equivalently, we could write this as watts per meter per degree Celsius. Because we have a delta T here, a change or a difference in temperature, Kelvin and degree Celsius are the same for a temperature difference. So I showed that in the previous video. Okay, so these are the units of thermal conductivity. So let's take a closer look at thermal conductivity. So the thermal conductivity is the constant K that we saw in the previous equation. And basically, the thermal conductivity of a material tells you how easily does heat flow through that material. So if you have a very large K value, then heat will easily flow through that material. If you have a small K value, then it's very resistant to heat flowing through it. So if we look at this table here, we have different materials and the value of K, the thermal conductivity, listed for each one of those materials. And in the table, things are arranged from high K values on top to low K values down here. So at the very top, we have things like copper, which has a thermal conductivity of 399 watts per meter per Kelvin, and things like gold and aluminum and iron. All of these metals that we see up here appear to be very good thermal conductors. And that should agree with your experience, because we make things like pots and pans out of metal. We want them to be good thermal conductors so they can cook our food. On the other side of the table, down here, we have things like air and cork and wood and plastics. These have very low values of K. They're not very good thermal conductors. We call these materials thermal insulators because they prevent heat from flowing through them. And we can use them for insulation in certain cases. Okay, so that's really the spectrum we see. We have high K values as thermal conductors and low K values as thermal insulators. Now, it also happens that these materials are also good electrical conductors, and these materials down here are also electrical insulators. So electricity also easily flows through these materials, whereas it doesn't easily flow through these materials. Now, that's not just a coincidence. There is a relationship between thermal conductivity and electrical conductivity, but we're not going to get into that here, but I just wanted to point it out. So let's take a look at an example here. Let's say we have a rectangular glass window, which has dimensions 2 meters by 1.5 meters, and it's 3.2 millimeters thick. The thermal conductivity of glass is K equals 0.84 watts per meter per Kelvin. Let's suppose that the temperature of the air outside your window is 14 degrees Celsius, and the inside temperature is 15 degrees Celsius inside of your house. So what is the rate of heat loss via conduction through the window? And at this rate, how long would it take to lose 1 million joules of heat through the window? So pause the video, try to work this out using the equation that I showed you earlier. See if you can get it, and then come back to the video so we can do it together. Okay, so let's work this out. We'll draw the window. So it's a rectangular piece of glass where this side length is 2 meters, and then we have 1.5 meters on this side, and then the thickness of the glass, that thickness is 3.2 millimeters, and that's delta X. So here, delta X is 3.2 millimeters. The area A is just the area of the sheet, which we can calculate in a second. But let's indicate the temperatures involved in this process. We have, let's say this is the inside of the house on the right. So the high temperature is 15 degrees Celsius. And then, so out here on the left is the outside of the house. The cold temperature is 14 degrees Celsius. So because we have this temperature difference between the inside and the outside of the house, heat is going to be flowing. And it's going to be flowing in the direction from hot to cold. So there's our Q right there. Or let's call it delta Q to be more precise. Okay, so that's the direction that heat is flowing. Now, if we want to find the rate of the heat loss, so we're losing heat from the house, that rate is delta Q over delta T. It's the amount of heat we're losing per unit time. So how about we call that R, okay? R is delta Q over delta T. And for now, I'm not interested in the negative sign. I just want the absolute value of this. So that's going to be equal to K times A times delta T over delta X. Okay, so K is the thermal conductivity of the glass. That's 0.84 watts per meter per degree Celsius. A is the area, so that's going to be 2 meters by 1.5 meters. Now delta T is the temperature difference between the inside and the outside. 15 degrees Celsius minus 14 degrees Celsius. And then we're going to divide that by delta X, the thickness of the window. That's 3.2, 10 to the minus 3 meters, because a millimeter is equal to 10 to the minus 3 meters. Okay, so we'll crunch these numbers, and we'll notice that the unit we're left with is watts. And this comes out to about 788 watts, but we're going to keep 2 sig figs on that and round it to about 790 watts. Now, a watt is the same as a joule per second. So that means every second that passes, we're losing about 790 joules worth of energy through the window, okay? So the second question is, how long would it take to lose 1 million joules of energy through the window? Well, for that, we're going to go back to our original equation. So if this rate of heat conduction is equal to delta Q, the heat that flows through the window, divided by delta T, the time it takes, if we want to solve for the time, delta T, that would just be equal to delta Q divided by R, where in this case, we're talking about 1 million joules, or 10 to the 6 joules worth of heat going through the window. So if we divide by the rate, that's 788 watts, which is the same as joules per second, we can see that this comes out as a unit or an amount of time. So we have 1,269 seconds. If we convert that to minutes, because in every 1 minute we have 60 seconds, what we get is about 21 minutes. So it takes about 21 minutes in time to lose 1 million joules of energy through the window. So let's take a look at another example of heat conduction. So here we have a cube of ice, which is at 0 degrees Celsius. The length of each side of the cube is 27.5 centimeters. Now this cube is resting on a square aluminum plate. The plate has dimensions 27.5 centimeters by 27.5 centimeters, and it has a thickness of 1.35 centimeters as shown here. So what we're going to do is we're going to heat up the bottom of the plate so that its temperature is 175 degrees Celsius down here. But remember, up here, the temperature is still 0 degrees Celsius. So how long would it take to melt all of this ice? And then as a follow-up, how long would it take if this plate were made of glass? Okay, so instead of aluminum, if this plate were made of glass, how long would it take to melt all of this ice? So we need to know that the thermal conductivities for aluminum and glass are 237 watts per meter per Kelvin for aluminum and 0.81 watts per meter per Kelvin for glass. We also need to know that the latent heat of fusion for ice is 3.34 times 10 to the 5 joules per kilogram, and the density of ice is 0.917 grams per cubic centimeter. So there's a lot of data that's going to go into this, so I'll show you how to make the calculation. But one thing we're going to assume is that all of the heat that's transferred to this ice is via conduction through the plate. So we're going to ignore any other type of heat transfer that may be happening. We're going to assume it's all just conduction through the plate. And with that said, let's work it out. So I'm going to start by drawing a picture. I'm only going to show the plate in this picture and not the block of ice on top of it, just so things don't get too cluttered. But here's the plate. The length of each side of the plate is 27.5 centimeters. So 27.5 by 27.5 centimeters over here. The thickness is delta X, and that's 1.35 centimeters. So the temperature up here, where the ice is 0 degrees Celsius, whereas the temperature down here is 175 degrees Celsius. So what we're going to have is heat flowing through the plate like this, from hot to cold, and going into the ice. Okay? So the rate of heat conduction through the plate that's going to be given by delta Q over delta T. That's the rate of heat conduction, and we'll just call that R for now. And then just concentrate on the absolute value here, so don't worry about the negative sign. That's equal to K times A times delta T over delta X. So let's figure out what that is. Okay, assuming the plate is made out of aluminum, then this rate is going to be K, which is for aluminum 237 watts per meter per degree Celsius. A is the area of the plate, so it would be 0.275 meters squared, because it's a square area here. And then we take delta T, which is 175 degrees Celsius minus 0 degrees Celsius on top, and then divide by delta X, which in meters would be 1.35 times 10 to the minus 2 meters. So we have to convert from centimeters to meters to get this to work out. And what we'll find is the rate is 2.323. We're going to keep 3 sig figs on that, times 10 to the 5th power watts. And again, remember, a watt is a joule per second. Okay, so that's the rate of heat conduction through the plate. Now, a separate question is, how much heat do we need to melt all the ice? Well, that's our delta Q. Remember, for a phase change, like going from solid to liquid, as what's happening here, the latent heat is given by M times L. So we're going to take the mass of the ice times the latent heat of fusion in particular, and it's going to be positive because the heat is flowing into the ice. Okay, but we also remember that density is equal to mass over volume. Or in other words, rho is equal to M over V. The thing is, we don't know the mass, but we can easily figure it out because the mass would just be the density rho times the volume V. Now, for this ice cube, remember, it's the shape of a cube. So if the length on each side is L, the volume would be given by L cubed. So the mass is the density times the length of each side to the 3rd power. And I'm going to use that back over here in my delta Q expression. So the mass is the density times the length of the cubed to the 3rd power, and then times the latent heat of fusion. That's going to tell us how much heat we need in order to melt all of this ice. So let's work it out. We have delta Q equaling rho. That's the density of the ice. That's 917 kilograms per cubic meter. And then we have L, which is 0.275 meters to the 3rd power. And then we have the latent heat, which is 3.34, 10 to the 5 joules per kilogram. So meters cubed cancel, kilograms cancel, and we just have joules. So we have 6.369 times 10 to the 6 joules. That's how much heat we're going to need in order to melt all this ice. Okay, so how long will it take to melt all the ice? Okay, that's the question we're really trying to answer here. Well, remember, the rate of heat conduction is delta Q over delta T. It's the amount of heat flowing through the plate per unit of time. And if we want to know the time, that's just delta Q divided by R. So what's delta Q? 6.369 10 to the 6 joules. That's how much energy it's going to take to melt all the ice. Divided by R, which we calculated up here, is 2.323 10 to the 5 watts or joules per second. So we get an answer in seconds, 27.42, or about 27.4 seconds. So we're using a material, aluminum, to conduct the heat. So aluminum is a very good thermal conductor. That's why it takes not that much time to melt all this ice. But if we follow up and consider if the plate were made of glass instead of aluminum, basically what we're going to have to do here is recalculate R, recalculate the rate of heat conduction. Because here, let's go back to the top. R is equal to K times A times delta T over delta X. So let's copy that down. We have R equals K times A times delta T over delta X. The only thing that's changed is K. It's a new material, has a different thermal conductivity. So the K value for glass is 0.81 watts per meter per degree Celsius, like this. A is the same as before, it's just the area, 0.275 meters squared. And then the temperature difference is the same as before, 175 degrees Celsius minus 0. And then delta X, the thickness, is the same as before, 1.35 10 to the minus 2 meters. So if you calculate this, it comes out to 794 watts. That's the rate of heat conduction. It's much, much slower than if we're using aluminum. So as a last step, we have R equals delta Q over delta T, as we saw before, which means delta T is delta Q over R. We're still trying to melt all the ice, so the heat required for that delta Q is the same as before, 6.369 10 to the 6. But it's the rate of heat conduction that's changed. Now this is only 794 watts or joules per second. So this works out to 8,021 seconds, a lot longer than what we had before. Let's actually convert this to hours. In every 1 minute, we have 60 seconds. In every 1 hour, we have 60 minutes. So cancel out minutes and seconds. In hours, this will take 2.228, or about 2.2 hours. So it's a very big difference. Okay? If we're using glass to conduct the heat, it takes a couple of hours. If we're using a metal like aluminum to conduct the heat, it only takes about half a minute to melt all this ice. That's what we found. And let's do one more example. We have a metal rod of length L, which is heated to a temperature of 475 Kelvin at the left end, and it's kept at this constant temperature at the left end, and it's cooled to a temperature of 205 Kelvin at the right end. So what we're going to assume is that there's a temperature at each point along the rod, but that temperature stays constant, okay? So what is the temperature at the midpoint of the rod, right in the center? And then what is the temperature 1/3 of the length from the left end over here somewhere? And then as a final question, at what position along the rod is the temperature going to be 275 K? So again, the idea here is if we hold this end at a constant temperature of 475 K, and we hold this end at a constant temperature of 205 K, the temperature is going to be slowly decreasing as you go from the left to the right end. So that's going to be the key to figuring out all of these questions. So we'll start by drawing a picture. So this is the rod. And at the very far left end of the rod, the temperature is 475 Kelvin. So I'll say the temperature is T1. I'll label it as T1, 475 Kelvin. At the very far right end of the rod, the temperature, I'll label it as T2. That's 205 Kelvin. So there's a point in the middle of the rod. Let's call it point P. And we want to know what the temperature is at that point, okay? So the way we're going to figure this out is to realize that at point P, the temperature is constant. And that means the total heat flowing into that point is equal to 0. Because if there was a positive heat flow into that point, the temperature would be going up. If there was negative heat, the temperature would be going down. But if the temperature is staying the same, then the total heat flowing into that point is equal to 0. So how do we think about that total heat? Well, there's going to be a positive heat, so flowing into that point coming from the left side, because the left side is a higher temperature. We're going to have delta Q1 coming in from the left. But since the right side is at a lower temperature, we're going to have a heat flowing out of that point to the right, which we'll call delta Q2. So the idea is delta Q1, which is positive, plus delta Q2, which is negative, sum to 0 such that the temperature at that point doesn't change. So we'll label some other things on this diagram. First, we have a distance from the left side of the rod to the point. We'll call that delta x1. And then we have another distance from the point to the right side of the rod, which we'll call delta x2. So the rate of heat flow from the left side of the rod to the point, which we'll call delta Q1 over delta T, is equal to the rate that heat's flowing from the point to the right end of the rod, which is delta Q2 over delta T. Now, technically, one of those is positive, the other is negative. So when we take the absolute value, that's when they're equal. And so we'll use the equation for heat conduction on the left side and the right side. So on the left side, we have K1 times A1 times delta T1, make sure we use the absolute value here, divided by delta x1. And on the other side, I have K2 times A2 times delta T2, also absolute value, just make sure that's positive, over delta x2. Now here's the thing. K1 is equal to K2. It's the same material over here as it is over here. So it's the same thermal conductivity. And also, A1 is equal to A2. The cross-section is constant. So the cross-sectional area of this rod is constant throughout. So we can right away cancel out K1A1 and K2A2. The next thing we can notice is that if we're talking about the halfway point, then delta x1 is L over 2. And by the same token, delta x2 is L over 2, half the length of the rod in either direction. So let's plug that into our equation. We have delta T1, so that's going to be T1 minus TP divided by delta x1, which is L over 2. That equals delta T2, and we want to take the absolute value. So whatever this temperature is, it's going to be greater than 205 Kelvin. So if I want this to come out positive, I have to write this as Tp minus T2. So this temperature minus this temperature, it's going to come out positive. And then I divide by delta x2, which is L over 2. So L over 2 cancels. And I have T1 minus Tp equals Tp minus T2. So let's rearrange that. We have T1 plus T2 equals 2 times Tp. That is, Tp is just T1 plus T2 over 2. It's the average of the two temperatures. So you might have been able to guess that, but this is how it works out. So the average of the two temperatures is T1, which we said is 475 K, plus T2, which is 205 K, divided by 2. And what do we get? We get 340 K. So the temperature at the midpoint in terms of distance is actually halfway between the two temperatures. But now, what if we're not talking about the halfway point anymore, but if we're going a third of the length from the left end? Well, now, delta x1 right here is going to be a third of the length, and delta x2 over here is going to be 2/3 of the length. So in our equation, we have delta x1 is now L over 3, and delta x2 is now 2L over 3. So again, just want to show you what I'm working on. Up here we have delta T1 over delta X, which is T1 minus Tp over L over 3. That's our delta X. That equals delta T2 over delta X2. So that's going to be Tp minus T2. Once again, divided by 2L over 3. So that's what we need to solve for. So first thing we can note is that we can cancel out L and the 3. So I have T1 minus Tp equals a half times Tp minus T2. So I have T1 minus Tp equals a half times Tp minus a half times T2. Let's put the Tp terms on one side of the equation. So we'll add Tp to both sides. And then we'll add this term to both sides. So I'm going to have T1 plus a half T2 equals 3/2 Tp. So Tp is equal to, multiply through by 2/3. We have 2/3 T1 plus 2/3 times a half is 1/3 T2. Okay, that's what we have. So this would be 2/3 times T1, which is 475 K, plus 1/3 times T2, which is 205 K. And that works out to 385 K. So let's recap. At the very halfway point, the midpoint along the rod, the temperature is 340 K. And then a third of the way from the left end, the temperature is even higher. It's 385 K, as we just calculated. Okay, so there's one more question here. Where is the temperature, Tp, equal to 275 K? So here's how we're going to deal with this. Delta x1 is going to be some fraction of the length of the rod, which means delta x2 would be 1 minus that fraction of the length of the rod. So for example, if delta x1 is a quarter, then delta x2 would end up being 3/4 of the length of the rod, okay? And we're just going to figure out what f is. Whatever that fraction is, we'll find it. So using the same sort of setup as before, again, we have delta T1 over delta X1. So that's going to be T1 minus TP over F times L equals delta T2 over delta X2. So that's going to be TP minus T2 over 1 minus F times L. So cancel out L's and rearrange this. So let's multiply through by 1 minus F. So we have 1 minus F over F. And then divide through by T1 minus TP. So we have on the other side TP over T2 divided by T1 minus TP. Okay, so here let's simplify this. We have 1 over F minus 1 on this side equaling, okay, TP is 275 K minus T2 is 205 K. Divide by T1, which is 475 K, minus TP, which is 275 K. So what does this all work out to? Well, I have 1 over F is equal to 1 plus this big fraction here. So on top, we have 275 minus 205, which is 70. On the bottom, we have 475 minus 275, which is 200. So here, 1 over F is equal to 1 plus 7 over 20. In other words, 1 over F is equal to 27 over 20 because we can write 1 as 20 over 20. So that gives us 27 over 20. And therefore, F is equal to 20 over 27. So in other words, 20 over 27 is about 0.74. So what we're saying is T is equal to 275K at a point that's 0.74 L from the left end. In other words, over here somewhere, that's where we see the temperature go to 275K. Okay, so that's how you do this one. So we've gone over some of the modes of heat transfer. We talked about convection, which is typically how heat would be carried through a fluid. We've talked about conduction, which is how heat is carried through a solid material. And the last one to touch on is radiation. So radiation is when energy is carried from one place to another through electromagnetic waves. Now, when I say electromagnetic waves, that's just a fancy way of saying light. Okay, so if energy is being carried from one place to another through light waves, that's radiation. Now, a classic example of this is how Earth is heated by the sun. That's a process of radiation. Because if you think about it, the space between the Earth and the sun is not really filled with much matter at all. It's almost a vacuum. So there's not really conduction going on. There's not a solid object that links the sun to the Earth. There's not really any fluid between the sun and the Earth for convection to happen. This is all radiation. Okay, so the light emitted by the sun is heating the Earth. We're carrying energy from a high temperature region to a low temperature region through these light waves. That's how radiation works. And again, unlike convection and conduction, which require some kind of material for the heat to move through, with radiation, we can have perfectly empty space carrying light waves, and we can have heat traveling through perfectly empty space. So that's all I wanted to say about modes of heat transfer. The only one that we're really going to make any calculations with is conduction. We just don't have enough time to go into the details about how radiation and convection work, but hopefully you see what the concept is. And so that takes us to the final topic of this lecture, which is the laws of thermodynamics. Now again, here we're not going to go into a whole lot of mathematical detail. I just want to introduce you to some concepts. If you take Physics 47, we're going to go into a lot more detail about the laws of thermodynamics in that class. But here, I just want to give you an introduction. Okay? So we'll start with a question for the class. Consider the following hypothetical process. Let's say we have block 1, which is initially at 300 degrees Celsius, and it's in contact with block 2, which is initially at 600 degrees Celsius. So imagine that 1,000 joules of energy flows out of block 1 into block 2. So the heat is flowing from the cold block into the hot block. And that increases the temperature of block 2. Let's say it goes up to 601 degrees Celsius. And it decreases the temperature of block 1 to 299 degrees Celsius. So we know that doesn't really happen. Heat's kind of flowing the wrong way here. But what I want you to think about is, does this process violate conservation of energy? So if you think about the process I just outlined here, does that violate conservation of energy? Yes or no? So pause the video, think about this, and see if you can come up with an answer. So, does this process violate conservation of energy? Well, the answer is actually no. Conservation of energy is not violated. In this process that I'm showing you here. And the reason is pretty simple. Energy is just moving from one place to another. It's not like we've created energy out of nothing or destroyed existing energy. Energy is actually conserved here. So if we think about it, block number 1 is losing 1,000 joules of energy because heat is flowing out of that block. So we can say for block 1, delta E1 is minus 1,000 joules. So it lost energy. And that leads to the temperature going down. For block number 2, it gains that same amount of energy. So delta E2 is positive 1,000 joules. It gained energy. And as a result, its temperature went up. So the total change in energy in this process, delta E1 plus delta E2 is just 0, which means energy is conserved. So there is obviously something wrong with this process. Heat should not be flowing from a cold object to a hot object. But the reason that can't happen is not conservation of energy. There's some other principle that explains why this can't happen. And that takes us to the laws of thermodynamics. So I'm going to tell you about the first law and the second law of thermodynamics, which we'll study in a lot of detail if you take Physics 47. But here I'm just going to outline the basic concept. So the first law is basically just conservation of energy. The first law of thermodynamics says that the total energy of the universe is conserved. Energy can't be created or destroyed. It can only be transferred from one object to another or transformed from one type of energy to another type. So if you take 2 billiard balls and watch them collide on a pool table, they're exchanging energy with each other. There's energy being transferred from one to the other. And if you drop something, you're converting potential energy into kinetic energy as it falls to the ground. So all of these things can happen. But the point is the total energy, if you take the sum total of all the different energies that are out there, that's conserved. The second law says that the total entropy of the universe always increases. So first of all, I'm going to explain what entropy is, so we'll get to that. But notice how this is not about something being conserved. This is about a quantity that's always increasing. It's always going up. It's not conserved. It's always increasing. So entropy is given by the variable S. So if you want to put this in an equation, it says delta S, the entropy change for the universe, is always positive because it's always increasing. So then what is entropy in the first place? Well, we can think of entropy as the level of disorder within a particular system. So, for example, let's say the system we're thinking about is this pile of bricks. So it's in a highly ordered state when I stack the bricks on top of each other to form a pyramid like this. This would be a low entropy state, low disorder. On the other hand, if the bricks were just randomly scattered all over the place, that would be a highly disordered state. It would be a high entropy state. So if we're going from the nice orderly stack of bricks to this random pile of bricks strewn all over the place, we're increasing the entropy of the system when we do that. So if we want to be a little bit more formal about what entropy means, we have to think about microstates. So a microstate is what a system looks like on a microscopic level. So it's a description of the position and the velocity of every single particle in that system. So the microstate of a system is never something that we actually know exactly. If you think about it, let's say I have a glass of water. That glass of water contains something like 10 to the 24 water molecules. So there's just no way I'm going to be able to keep track of the position and the velocity of every single one of those molecules. So what I can know is the macrostate of the system. So the macrostate is defined by the large scale properties of the system that we can actually measure, things like the temperature of the system and the pressure. So that's the difference. Microstate, that's what it looks like on a microscopic level. It means we know exactly where and exactly how fast every particle is moving. The macrostate is a little bit less detailed than that. It's just what can we measure on the large scale, like temperature and pressure. So I want to give you sort of an analogy for microstates and macrostates that's pretty easy to understand. So let's say that I flip a coin 4 different times. So I flip a coin 4 times in a row. There are a bunch of different ways that can come out, but the number of times that heads came up can be considered the macrostate. So if I flip a coin 4 times and I get heads 3 times, that's my macrostate. On the other hand, the exact outcome of every single coin flip would be a microstate in this analogy. So if I tell you that I got tails on the first flip, heads on the second flip, then tails again, and then heads again, that would be an example of a microstate. Okay? So let's actually fill out this table. I want us to look at, for each one of these macrostates, what are the corresponding microstates? So for example, if I flip a coin 4 times and I get 4 heads and 0 tails, there's only one way that can happen. That's if I get heads on the first flip, heads on the second flip, heads on the third flip, and then heads again on the fourth flip. That's the only string of 4 flips that gives me this outcome. But on the other hand, if I look at the macrostate where I get 4 heads and then 1 tails, there are actually 4 different ways this can happen. So I can get tails on the first flip and then heads, heads, heads on the next 3. Or I can get heads, then tails on the second flip, and then heads, heads after that. Or I can get my tails on the third flip or on the fourth flip. There are 4 different ways that this can happen, where I get 4 heads and 1 tails. So we have 4 different microstates that correspond to this macrostate. Okay, I can also get an even split. I can get 2 heads, 2 tails. There are actually 6 different ways that that can happen. So I can get 2 tails followed by 2 heads. And then I can get 2 heads followed by 2 tails. I can get tails, heads, heads, tails. Get heads, tails, tails, heads. Or I can get tails, heads, tails, heads. Or I can get heads, tails, heads, tails. So there are 6 different ways I can get that even split. What we say is there's 6 different microstates here. Okay, when it comes to getting 1 heads, 3 tails, there are 4 different ways that can happen. So you can get heads on the first flip followed by 3 tails, or you can get heads on the second flip, or on the third flip, or on the fourth flip. Again, there are 4 different ways that can happen. And then if we get 0 heads and 4 tails, there's only one way that can happen, just to get tails, 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 tails. So let's actually count up these microstates. For 4 heads, 0 tails, there's only 1 microstate that corresponds to that. For 3 heads, 1 tails, there's 4 that correspond to that. For the even split of 2 heads, 2 tails, there are 6 microstates that correspond to that. And for 1 heads, 3 tails, there are 4 microstates that correspond to that. And then finally, 0 heads, 4 tails, there's only 1 microstate that corresponds to that. So the total number of microstates is 1 plus 4, that's 5, plus 6, that's 11, plus 4, that's 15, plus 1, that's 16. So there are 16 total microstates here. Now, what is the probability of each one of these outcomes? Well, it's 1 in 16 to get 4 heads, 0 tails, because there's only one way that can happen out of a total of 16. But for 3 heads, 1 tails, there are 4 ways that can happen out of a total of 16. So the probability is 4 over 16, or 1 over 4. For this one, there are 6 ways that can happen. So the probability is 6 over 16, or 3/8. For this one, there are 4 ways it can happen. So the probability is 4 over 16, or 1/4. And then finally, for no heads, 4 tails, there's 1 way that can happen. Out of 16, the probability is 1 over 16. And so here's the takeaway point of this analogy. If I think about all of the possible microstates of a system, if I actually just list them all out, I can use that to calculate the probability of getting a certain macrostate. Okay, that's what I want you to see from this analogy. And so how does this all tie back in to entropy and the second law of thermodynamics? Well, in thermodynamics, we typically assume that all possible microstates of the system are equally probable. So any microstate that you think of is just as likely to happen as any other. But we've seen in the coin flip example that it's possible for many different microstates to correspond to the same macrostate. So for example, we saw there were 6 different ways you can flip a coin 4 times and get 2 heads, 2 tails. So your system can be in many different microstates that on the large scale look exactly the same. That's the idea. So let me give you an example of this. Let's say we have a box of gas, and the gas molecules are basically evenly spread out throughout the box. So if I take 2 of those molecules and I just switch them, so I take this one that's labeled in yellow and I switch it with this one that's labeled in red, we're still in the same macro state. On the large scale, it still looks like the gas is evenly spread out throughout the box, but it's a different microstate. Okay, and you can actually think of a lot of different ways to switch things around, to rearrange things in the system and still be in the same macro state, for everything to still look the same on the large scale. So that brings us to the probabilities that we talked about earlier. The probability to find a system in a given macrostate is this. We simply take the number of microstates that correspond to that macrostate, and then we divide that by the total number of possible microstates. That's exactly what we did with the coin flips. So in shorthand, we'll say this is equal to W. W is the number of microstates that correspond to our macrostate, and N is just the total number of possible microstates, period. So the probability is just W over N. And so with these concepts in mind, we can now write down a formula for entropy. So this formula was developed by Ludwig Boltzmann back in 1875. And here's what it says. S is the entropy of a system in a given macrostate. That is equal to Kb times the natural log of W. Kb is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin. This is the same exact constant that we find in the ideal gas law. And W over here is the number of microstates that correspond to a given macrostate, just as we said earlier. So basically what this is saying is that entropy only depends on W. Kb is just a constant. So entropy depends on the number of ways that a system can be rearranged, but still look the same on the large scale. So how many different ways can we rearrange the particles and it still looks the same macroscopically? That's W, and that's what entropy is dependent on. Now this formula is actually what appears on Boltzmann's tombstone, so it's a really important formula for him. If you visit his gravesite, you'll see this engraved on his tombstone. And this takes us to the second law of thermodynamics. Basically, as we said earlier, the second law says that the entropy of the universe is always increasing. In other words, delta S for the universe is always going up. It's always increasing. That means that high entropy states are more probable than low entropy states. So higher entropy states with more disorder are more probable. Naturally, any system is going to tend to evolve from low entropy to high entropy. That's really what the second law tells us. So let's take a look at a few examples to really understand the concept and how it applies. So here we have the diffusion of dye in water. So if we take a couple drops of dye and put it into a container of water, we know what happens. Over time, the dye spreads out. It diffuses into the water, and after a really long time passes, you'll see it completely evenly mixed in with the water. This is the final state, and it never unmixes and goes back to this original state. So we can understand why that happens in terms of the second law of thermodynamics. There are just way more microstates where the dye molecules are evenly mixed like this, compared to microstates where they're all concentrated in one place like this. So this is a high entropy state, and this is a low entropy state where the dye is all concentrated in one place. But according to the second law, entropy always increases. So if we start off in this low entropy state, we're going to have to eventually reach this higher entropy state where everything is evenly mixed. And once we're there, it never goes back. So once we reach this equilibrium, we never go back to the starting state, okay? Because that would violate the second law. That would mean entropy has decreased, and we never see that happen. Another example is when we reach thermal equilibrium. This is one of the very first things we talked about in this lecture. The idea that if you have two objects, one of them is at a high temperature, the other is at a low temperature, and you let them touch, you let them exchange energy. If you wait long enough and you wait for heat to flow from the hot object to the cold object, eventually you'll reach thermal equilibrium where the two objects have the same temperature. So why does that actually happen? Well, again, it has to do with the second law of thermodynamics. There are far more microstates where the energy is equally shared by the two objects and they have the same temperature, compared to microstates where one object is hogging all of the energy. So energy is concentrated in the hot object, there's very little energy in the cold object, there just aren't that many microstates that correspond to that. So naturally, the system is going to evolve from this low entropy state, where we just have two different temperatures, to this high entropy state, where the two objects have the same temperature and they're in thermal equilibrium. And again, once we reach thermal equilibrium, that's not something that goes back to the original state. Because if we have, the two blocks at the same temperature, we'd have to actually decrease entropy in order to get back to this original state. So that doesn't happen, it violates the second law. That's why heat flows from hot to cold and you reach equilibrium, but it doesn't flow the other way. So that takes us to a really fascinating but sort of depressing idea called the heat death of the universe. So if we take the second law of thermodynamics very seriously, the idea that the entropy of the universe is always going up, well, we expect the entropy of the universe just continually increases over time. But is there any sort of endpoint to that? Does the entropy just go up forever and ever and that's it? Or does it sort of max out at some point? So the idea of heat death is that at some point we expect the entropy of the universe does max out. It reaches a maximum value. And according to calculations that theorists have made, this isn't going to happen for a very long time. Something like 10 to the 100 power years is how long we'd have to wait to see the heat death of the universe. But what does this look like? What does it look like when the universe reaches this state of maximum entropy? Well, the first thing to note is that the universe itself reaches thermal equilibrium. Remember, thermal equilibrium is when things reach the same temperature. So if the universe as a whole is reaching thermal equilibrium, that means every single part of the universe has the exact same temperature. There are no longer any temperature differences between different parts of space. Now, right now, there are definitely temperature differences between different parts of space. You have things like the sun, which are like 6,000 Kelvin at the surface. You have places like the Earth, where it's like 300 Kelvin at the surface. And then just in empty space, the temperature is almost absolute zero. It's like 3 Kelvin. So when heat death is reached, those temperature differences between different parts of the universe are going to be gone. Everything's just going to be in equilibrium. And that also means the energy of the universe is just spread out. It's perfectly evenly spread out. There's no energy concentrated in one place more than another, just evenly spread out. And unfortunately, what that means is nothing interesting can really ever happen again, because all the matter and the energy in the universe is in perfect equilibrium. It's all perfectly spread out. So you don't have any interesting structures anymore, like stars, galaxies, and humans, things that make the universe interesting. You just have a sea of particles completely evenly spread out, and that's it until the end of time. That's the idea of heat death. And it's an idea we should take pretty seriously. So what does this look like? Heat death is expected to happen in a really, really long time, 10 to the 100 power years. It's some unimaginable amount of time. How do we actually get there? What's sort of the timeline between now and then, and what sort of changes happened in the universe for us to get there? So we're going to take a look at a timeline which shows us how much time has passed since the Big Bang. So how many years have passed since the beginning of the universe, in other words. And we're going to look at some important events that are expected to happen in the future of our universe. So at the very beginning of this timeline, we have today. So it's been about 10 billion years, or 10 to the 10 years since the Big Bang. And we're currently living in what's called the stelliferous era of our universe. That's just a fancy way of saying that the universe is currently dominated by stars and galaxies. But that's not going to last forever, because the thing about stars is they have a finite lifetime. Every star will eventually die. And furthermore, the material that's needed to make new stars is eventually going to be depleted. We're going to run out of gas to form new stars eventually in our universe. So in about 10 to the 14 years, all star formation in the universe is going to stop. No new stars will be formed after this point. And then we'll be living in what's called the degenerate era. So I'm not talking about the 1970s here. I'm talking about an era in the future of our universe where the universe is dominated by the remnants of dead stars. Okay? We're talking about things like white dwarfs and neutron stars and even black holes. But here's the thing about black holes. They actually don't last forever either. Every black hole is eventually going to evaporate. So when you have a really gigantic black hole, it very, very slowly evaporates. It gives off this radiation called Hawking radiation, and that makes the black hole slowly shrink over time, get smaller and smaller. Eventually, the black hole is completely gone. But this process takes a really, really long time, okay? So in about 10 to the 100 years, every black hole in the universe is going to evaporate. And there's going to be nothing left at that point except a sea of particles, okay? That's when we reach heat death. All that's left is very low energy particles. All the energy of the universe is evenly spread out. Everything is in perfect equilibrium. And again, after that, there's nothing really new that can happen, okay? It's just pretty much, for all intents and purposes, the end of the universe. So that's how we get from the present day to heat death. But again, don't really worry about this because it's going to happen in a really, really long time. So way longer than we'll be around for. So the last thing I want to touch on here is called the arrow of time. So this is the idea that there's a direction to time. So time always marches forward, it never goes back. And that's kind of a mystery from the standpoint of physics. We want to be able to explain why is it actually impossible to reverse time and then go back to the past. Now, the reason this is kind of a mystery is that most laws of physics that we know about appear to be what's called time symmetric. That means there's no distinction in the laws of physics between time going forward and time going backwards. So in other words, any process that can happen forward can also happen in reverse. Now, if you think about just any equation you've seen so far in physics, like F equals ma, in that equation, there's just no distinction between time going forward and time going backwards. It's not built into that equation in any way. And the same holds true for most laws of physics that we know about. The second law of thermodynamics appears to be the only exception to that we know about. So it could be that the only reason we perceive time going forward and never time going backwards is the second law of thermodynamics. It's because entropy is increasing. That's what's responsible for the arrow of time. So if you think about this on the large scale, in terms of the universe as a whole, if entropy is always increasing, that means the entropy must have started off at the Big Bang with a very, very low entropy, because the entropy has just been going up ever since then. So the entropy starts off very low, it increases over time, and as we see that entropy increase, that's what might be responsible for the idea that there's an arrow of time, that time goes forward. But then that begs the question, after the universe reaches heat death and entropy just maxes out, will there be any sort of meaning to the idea of time anymore? So these are real questions that physicists wonder about. I just wanted to sort of put that in your head as something you might study if you continue on in your physics education. So a lot of this thermodynamics stuff has a lot of really interesting applications. But anyway, that's all we're going to do in this video. Of course, we always have practice problems at the end of every lecture, so check these out as you study for the final exam. But we'll wrap it up here, so I'll see you next time. As always, take care, be safe and be healthy out there. See you later.